Let's practice now predicting products when we're doing alkene hydration and using this time oxymercuration-demercuration. So let's draw the structure of the substrate is the following. In here I have a D. What that D is the deuterium, an isotope of hydrogen. Chemically, the same. So we're going to consider that as if we had a hydrogen. But it's like labeling that position. So it's going to be important for us. So now, say conditions are oxymercuration. So first I have mercuric acetate and that with water. And then in the second step, I will do sodium boron hydride and basic conditions. That is my second step. Let's make this longer. Okay. So when we're doing that, remember that we formed the mercurinium ion. So when we do the mercurinium ion, say here, inserting that. So let's do wedge, HG, and here I'm gonna have the metal right there. And here I have a deuterium. So this was on the plane. I am adding the mercurinium ion, mercuric acetate on the top part. Well, now, once I have that, we want to remember that deuterium is like if we had hydrogen. So this carbon is the more substituted, this is the least substituted. So as if we have hydrogen. Therefore, the nucleophilic attack is going to happen at the more substituted because this carbon has a metal group. So you're going to have a nucleophilic attack and this will open up. This is above, this is going underneath. So the nucleophilic attack. So when we have the products, this is going to open towards that way. And here you will have the D, HG, this is D, your deuterium. And here you will have the underneath where we'll have the OH. I'm going to draw OH already, so assuming that we already had the proton transfer. And we will have that metal is going to go on the wedge because the attack came from the back. So when I have that, and after we do the reaction, that demercuration, the final product is going to have here a D, an H. So we're replacing, in this step, we replace the mercury and acetate by an H. In here you will have metal OH. And since we can form the mercurinium ion above the plane, again, the plane of the molecule, and you can do above or under. So we can have that also in dashes. So we will make this plus the enantiomer, in which, of course, the configuration of the two chiral centers will be inverted. So that is how you would make the products. Now, I want you to see, again, a stereochemistry. You have added, what you added across the double bond, you added, it is a hydration, so you added this. In one carbon, which is the least substituted, you added the H. Here it is. And the other carbon, the more substituted, you added the OH. So you are hydrating, adding water. But what you added is, notice here, OH, let's do it here, the final product. OH is on dash, H is on wedge. So it is opposite side, because the nucleophile will approach opposite to the leaving group, so similar to what we see in SN2 reaction. So underneath, here's your, again, if the mercury in the cycle is above, then the nucleophile attacks opposite sides. So that's why you have that. And it is anti. And in the enantiomer, same thing, because you will form this in the dashes. You will draw that in dashes. So summarizing the reaction as we have seen before happens, this reagent, you will form the regiochemistry is regioselected Markovnikov because your final product has the OH at the more substituted and the H at the least substituted. It is Markovnikov, but is also anti. The mechanism, because the OH and the H end up opposite sides respect to that plane.